So a little bit brief about the project. This project is funded by Interact, and the project is called Interact is a network plus by funded by Made Smarter initiative, UK initiative, and it's also a UK funded project. And the project is about actionable insight. They call this funding type is actionable insight. What that means, I need to explain a little bit to kind of get the context right. Actionable insight means actually when as academic we publish paper. This work similarly is based on an academic work, and we published it was a tool I developed, or a method I developed during my PhD, and then further developed in a article which is cited here. If you're interested, I can forward this article to you. Often academic articles are very complex concepts, and as you can will see in this, we can go in very detail. So how do we make that academic output into something that is easily transferable, and business can use that knowledge, or kind of adopt that knowledge or understanding and apply that. So this funding is the transition where an academic paper, we produce something that translates that idea in a actionable form, and then they can apply. So the background for this, for giving this background is something I need to mention. This tool is not a commercial tool. This is a demonstration tool where the method I have developed will be demonstrated simple form using this tool. So you will see and get, please don't get disappointed the simplicity of the tool. So there are two purposes for the tool. Is one, to go through the steps that we propose, and second, to demonstrate how we can apply those steps in an application. And then if you're happy with this tool, you can or the process, if you want to adopt, you can learn from using the tool, and then you can get in touch with people that how to develop it further or get understand more widely. So the tool is about actually prioritizing verification, validation, and testing activity in new product development. So we'll get into that detail about the tool in a bit. So why we need to think about testing, verification, and validation now? So I like to demonstrate the reason with this diagram, which was developed uh, by energy transition and Victor Gale and Sharp. Um, what they presented here is that where we are in terms of low or zero emission technology market share, and they research in the measure, or I would say the core sectors, and we can probably relate ourselves in any of these sectors, and within this sector where we are in um, this transition of low carbon emission. And if we look at these diagrams, it's rightly present that many of the sectors are actually in the very early phases, where they are actually, the phase is called emergence phase, where they are moving actually towards adopting, not even adopting, they are developing the technology. There is, and if we are in that stage, there is the emphasis I wanted to put that there needs a very much coordinated development and testing of the activity. Some of the sectors probably have moved a little bit further, where they are in the diffusion phase, where the policies of and deploying and expand the deployment is expanding. Um, but none of the industry probably in where they need to be in the reconfiguration, where we have appropriate standards and the regulations and guidelines we need to kind of um, uh, use our technology widely and in a collaborative manner. So there are a lot of the challenges because we are in the early phase, because we don't know many of this technology, and how they will be incorporated into our product, and the adaptation, technological challenges, adaptation challenges. But also we need to develop it in such a way, it's a coordinated way. So with the link between supplier and customer and so on. There are a lot of challenges, but there are also opportunities, I think, because this is where we innovate. We probably position ourselves as well, how we want to be in the market, what's our brand, how we want to be recognized. So business has challenges, but I think it's a place where they have many opportunities as well. One of the example I like to bring as well, that how some industry or businesses have branded themselves, what they are proud about. So one example will be this meal, who are recognized, a German company. They are very much recognized for their durability of their product, and they proudly actually market their product or advertise their product, that they test their product for long. So it's a kind of confidence you get, or you share with your customer, that I can tell my product will last that long because I have tested for that. And this is their way of uh, the gaining that customers trust. So the example for this is just for us to think about that, how we of course do test, and challenging test, because it's expensive and so on, and no standards are telling us how to do it. But also we need to probably collaboratively work with academic, industry, and government, that how do we position ourselves, what's our brand would be. So m- moving to the next, we are a little bit ahead. We can of course open up. We are kind of 7 minutes ahead. We can open up any question we have for next 5 minutes. I will introduce Andrew in a bit, and uh, we before I give time to prepare, Andrew time to prepare and share his slide in the presentation. I would like to go for um, a quick survey, if you don't mind. So I'm gonna ask you a question, that how what's about, I mean, the people we have today here, what's our understanding in the process of verification, validation, and testing for the new product or technology? So to respond to this, please use your mobile if you can, using the QR code, or you can go to slido.com and then please use the code. It's on showing us on the slide. So I'm going to move, and you still can vote if you like, but I'm going to move to the next slide. Okay, um, that's really good. So I've got in the audience, I fairly understand the process. 47%, I have some knowledge. I have pretty good understanding. I'm learning, and no clue. That shows us, oh, we have a wide variety of, and it is still growing. So we can keep posting if you want. Um, Now, what I will do, the I'll introduce our keynote speaker, Dr. Andrew Halfpenny. So, Dr. Halfpenny has a PhD in mechanical engineering from University College London, UCL, and a master's in civil and structural engineering. With over 25 years of experience in structural dynamics, vibration, fatigue, fracture, he has introduced many new technologies to the industry, including AFib-based vibration, uh, fatigue analysis, crack growth simulation, and accelerated vibration testing. He holds a European patent for the damage monitoring tag, and developed the new vibration standard used for qualifying UK military helicopters. He has worked in consultancy for customers across UK, Europe, America, and the Far East, and has written publication on fatigue, digital signal processing, and structural health monitoring. He is a founding member of NFM PSE certification scheme and sits on the NFM's committee for dynamic testing. He is a visiting lecturer on structural dynamics with the University of Sheffield. So, my pleasure to introduce Andrew. Andrew, I will at this point stop sharing my screen, and if you please want to share your screen, and
Okay, can everyone see my screen all right and hear me?
yes, perfect.
Okay, that's good then. So I've titled my talk today, Qualification of High Value Based Products based on verification, validation and test. Let me just move my screen around a bit because as soon as I shared it, it suddenly moved everybody. So I'm just trying to find you all again. There we go. It's better. Okay, and I thought we'd start with a bit of fun because we're all used to looking at automotive and aerospace and things like that. But I thought we'd ask ourselves, when we're looking at verification, validation and test, let's do something a bit more exotic. I'd to look recently at how we might go about qualifying a nuclear fusion reactor. So let's hold that in our mind and see what are the steps in this. And so in particular, what I want to look at is the different steps in the process and also look at the tool sets that we have in those. And in particular, we're going to consider some of the limitations of FMEA, failure modes and effects analysis, and how we might improve on those for such devices as this. Here we go. So first of all, let's have a look at a motivation, an example. And this particular example comes from the automotive industry. So how would we qualify an electric vehicle battery system? Now, just to put this into context, this is a quote from a chief engineer of a large automotive OEM. He said to me this: in the past, if we had reliability issues with an engine component, we'd swap it out early under warranty. But EV batteries contain thousands of unserviceable components. They have a mandatory minimum 10-year or 150,000-mile warranty. And if there's a reliability issue here, it could sink the company. So that just shows the magnitude of the challenge ahead. He went on to say, in the past, we would select the warranty period based on market forces and over 50 years of historical maintenance data. But today, warranties are dictated by politicians for brand new concepts with no historical data whatsoever. So you can tell really how passionate he is about the challenge that lies ahead. If we look at the pain he's targeting, we can see that it's driven really by lots of new technologies and new materials being introduced. The components are really expensive, so failure can be hugely expensive to remedy. There's long warranty periods which are outside of his control. There's new territories and new ways that people are driving their vehicles, which we don't know about. And all this is being then driven by net zero requirements. And the ultimate pain is if we get this wrong, we could bankrupt a large OEM. So what's the solution look like? Well, my friends who work in reliability put it this way. For a duty cycle of 10 years, I require reliability exceeding 95% at a confidence level of at least 90%. And I really like this statement. It's got three parts. First of all, the duty cycle. We're specifying how long we want the product to survive. In this case, we've got calendric aging, 10 years. Or we've got a usage aging as well, 150,000 miles. So we've specified a period. We've also got a reliability target. Now, we like to talk about reliability because it's a positive number. 95 is a big number. That's good and reliable. But what it really means is that I want fewer than 5% failures. In other words, I'm going to budget for up to 5% failures in this, but I really don't want it to go above that. That will break my budget. And that's where the confidence level comes in. I want to be at least 90% confident I'm not going to blow my budget on this. So we've got these three things coming in, and this then specifies our reliability. We just have to remember, though, it wasn't many years ago that we didn't have to do this. A few years ago, we knew all about car engines and we incrementally improved them. And the engineer told me, he says, in the good old days, all I had to do was pass the sign-off test. Now I don't even know what the sign-off test looks like. And it's not just the automotive industry that face this problem. Net zero transformation through the whole of transport is having a massive impact and forcing companies to do things they've never done before. So if we look at aerospace, for example, then there's a lot of eVTOL, electric vertical takeoff and landing. So on the left, you can see an unmanned drone. But we're also going for manned aircraft, and we're also looking at autonomous transportation as well. So the pilot doesn't pilot, it does itself. So again, a hugely valuable and very significant thing going on there. And of course, when we look at our friends in the automotive, we notice we're going back almost to where we were 80 years ago. About a century ago, automotive was kicking off, and we didn't really know, are we going to have steam powered cars? Are we going to have battery powered cars? Are they going to be petrol, or are they going to be gas? It was still being decided. Yet it started that the internal combustion engine really took over. And today we're in a position where we're not really sure where we'll go. We've got wholly electric, battery electric vehicles, but we've also got internal combustion engine as well. And we've got that hybrid electric. And in the middle, there's the plug-in hybrid as well. It combines a battery and an engine. And of course, we've still not ruled out hydrogen. So on the left here, we can see a fuel cell electric vehicle. Now, again, fuel cells are really expensive. We've got to get this right. And fuel cells are very good, very efficient at low power operations, but they're not very efficient when the power requirements are high. And that's where we're now looking at using an internal combustion engine which is fueled by hydrogen. So same hydrogen, but two completely different concepts of how they work. So where we are at the moment is a really exciting time. There's lots of change being demanded through net zero, but there's also lots of uncertainty, and the value of these things are very high. Now, somewhere we've got to get that electricity. So that's where my little example here comes from of a nuclear fusion reactor. So on the left here, we can see the inside of a tokamak nuclear fusion reactor. And the guy there is doing some building, so he's there for scale. On my right, I had a little bit of fun here because I didn't really have a good picture of a tokamak. So I asked the AI engine to generate one. It came up with some really wacky ideas, but I particularly like this one because at least it's actually the right shape. So here's my AI generated view of a tokamak reactor from the outside. Now, the tokamak reactor is really challenging if we want to qualify it, because inside we're heating plasma to 100 million degrees Celsius. Now, obviously, we've got to keep that plasma in line, and we can't do that physically because anything that came into contact with this, bearing in mind it's 7 times hotter than the center of the sun, is instantly going to vaporize. So we keep it there by using an electromagnetic field. But that electromagnetic field is generated using superconducting magnets. So we're now looking at a temperature of minus 270 degrees Celsius or thereabouts. So what we've got in for a distance of about 2 meters is materials which have to survive a temperature gradient between minus 270 degrees near absolute zero and 100 million degrees, 7 times hotter than the sun. So this makes it the largest temperature gradient in the known universe. And this is what engineers are being tasked to qualify today. Oh, and did I also point out it's under a heavily neutron irradiated environment. So how the material properties change with that neutron irradiation over time is also an uncertainty. So here's our challenge. How would we go about qualifying this high risk, high value product? And in particular, we want to look at, so what's the process? What steps will we follow? What tools do we have today? And how might we develop those further? But don't worry, it doesn't have to be a tokamak reactor. It could be an electric vehicle battery, or a zero emissions excavator, or a fuel cell, or an eVTOL aircraft. It could be the autonomous control system in the new electric car, or it could be your brand new energy rating A washing machine. The same approach applies. So let's have a quick look at an example of verification, validation and test applied in the automotive industry. How would we qualify this electric vehicle battery system for vibration, for example? Well, first of all, we know an awful lot about cars and how they travel over the road and vibration. So maybe we would think about going to a historical test standard. However, these historical test standards are based on internal combustion engines, they're based on older vehicles, and are you really going to put that much emphasis on a standard and which may be risky? So what people are doing is say, yes, we're going to meet the standard, but we're also going to do our own research as well. A friend of mine who's a tech specialist from one of the large American automotive OEMs, he once described the situation like this. He says, there are three people who are really interested in my vibration qualification. I have simulation engineers who design components that don't break. I have test engineers who try to break them. And then I have the target customer who, for some reason, ultimately succeeds. So what we need to do is measure what the target customer is doing. Then we'll generate a statistically representative qualification test for that. And then we will simulate the test. In this way, if there's a break in any of this chain, we know where to go. So if the simulation works, but the test fails, what was wrong with the simulation? Why isn't the simulation not matching the test? And of course, if the test works, but the customer doesn't, what's happened here? Is this our statistical understanding of the customer? Is it the fact that this customer is in the 5%, for example? Or maybe this customer is now using the vehicle for something we didn't develop and now we need to take that into account. So the approach, first of all, is to do a statistical target customer analysis, measure vehicles that customers are doing. Now, as you know, we can't measure everything on a customer vehicle. There'd be wires hanging everywhere and they would all fall off. So we use minimal instrumentation. We just want to find out what they're doing with it. And the way we do that in a car is to turn customer usage into a proving ground schedule. So a proving ground contains lots of different surfaces. And what we're doing is we're saying this customer in North America is equivalent of this many miles on an A-class road, this many miles on a D-class, this many miles going over potholes, and this many on pave, and so on. And when we add them together, that actually gives us the life of that battery in that vehicle. So what the proving ground does is it makes it scientifically reproducible. On the proving ground, we can put lots of advanced measurements instrumentation to gather that data. So having gathered those data for a component like our battery, we can then go and develop an accelerated qualification test. So this is using one of our vibration shaker tables, and we've used our software to generate that test. This test contains statistically the same amount of damage as our 95th percentile customer will see, but we'll do it over a few hours rather than over the next 20 years. And then the final step from our tech specialist was we now simulate the qualification test. Because if we built a simulation model and we apply it to the test, that enables us to use both to verify that our simulation's working correctly. And now we know that our simulation's working correctly with the test and we've got test evidence, we can combine both of those in order to validate our design. So we're validating this reliability target, in this case, using a properly verified simulation model. So let's just put it a slightly other way. When we talk about verification, validation and test, that leads to product qualification. I've just reversed some of these definitions and chose some definitions here from papers. When we talk about validation, we're talking about, are we designing the right product? And when we talk about verification, we're saying, are we designing the product right? All we've done is reverse the two words. So validation is designing the right product. Will it do what it's meant to for as long as it needs to? And the verification is, are we doing that right? So do simulations match tests, and do tests match real usage? So testing is a major part of this. So if you imagine, we start off with a simulation, and that simulation is used to design and optimize components. But we need to make sure the simulation's right. So here we're going to do virtual testing and physical testing. The virtual test simulates the physical test. In other words, you simulate that component mounted in the physical test fixture. And then the physical test runs in parallel with that. And then we can take measurements from the physical test and ensure that our virtual test, our simulation's running well, and we can refine that model. When it comes to actually validating the component now, we use both of those. You see, physical tests are expensive and they take a long time, so we might not do everything. But if we know our virtual test is right, the simulation model can take over. So we can combine both of those to validate the component. So here we see, in the initial design, we use simulation. Then when we verify the design, we use a combination of virtual test based on simulation and physical test, and we iterate in order that we get a really good simulation. And then we use the combination of both of those in order to validate and qualify our component. So what does that look like in terms of a tool chain? So I've drawn this using three simple bubbles here. In bubble one, we're looking at the initial design and the initial qualification using verification, validation and test. As we start then to get that fixed, we'll go into the next stage, which is full prototype qualification. And we'll see that with the modern tool chain, this can actually extend into the operational phase too. And of course, when we talk about any component, whether it's on an electric vehicle, electric aircraft, or in tokamak reactor, we also have to consider what are we going to do with those components when they retire. So we'll also consider the circular economy. So first of all, if we go into the top bubble, where are we going to start? If we're going to qualify a tokamak reactor, where do we start? And actually, after thinking about it, I thought FMEA was a really good place to start. Why is that? So FMEA is failure modes and effects analysis, but the key thing is it brings people together. Now, I don't know about you, but I don't know a huge amount about the physics of nuclear fusion, apart from what I've read on the internet. But I do know people who do know that, the nuclear physicists who are working on this. There's materials that are being used here which I don't understand how they work at those temperatures, but I know a metallurgist who can help. FMEA is all about bringing people together, and it also is about capturing their knowledge in a way that democratizes that knowledge so other people can learn from it too. And ultimately, FMEA for me is about identifying risk. So how does that work? So FMEA, first of all, it's not a document or a program. It's a process, and it's a process of bringing people together. And what they're going to do is, first of all, it's helping us to understand this new domain, understand the anatomy of a fusion reactor. What are all the parts? What do they do? How might they fail? What would be the consequence if that failed? What precautions do we have in place? What are the known unknowns at this stage? And how would we go about qualifying what is and isn't acceptable in the form of a test? So FMEA isn't just a program or a spreadsheet or a document, it's an entire process of managing that meeting and distilling the information and knowledge. And it's actually a really good process. So the definition of FMEA is it's a structured and methodical approach to identify and prioritize risk. And when we do it, it looks a bit like a spreadsheet. We've got columns with various stages through, and rows are each individual fail mode, if you like. And what we do is we go and we identify every single component, every item that makes up this tokamak reactor. And the first thing we do as a group is we say, what is the function of this component? What is it supposed to do? Then we look at the failure modes. What would prevent it from doing that? And there may be many different failure modes, as we can see in this little example here. Now, each failure mode has a severity. If this were to happen, how bad is that? And believe me, at 100 million degrees, if something goes wrong, it could be pretty serious. So we usually rate them as numbers 1 to 10. 1 is not serious, 10 is this could be a major catastrophe here. For each of those failure modes, there may be a number of root causes that can lead to it. So for each root cause, we want to write it down. We also want to look at what is the likelihood of that. Again, score it just 1 to 10. This is a very qualitative state operation at this time. We've not got numerical measurements. We're just enumerating them with our opinion from a team of experts. We also want to say, how easy would this be to detect? Because if we can detect it early, we can remedy it. But if it's really hard to detect, like some fatigue issues, that's a real problem. So again, we can rank it. And then there's a process called the risk priority number, which simply multiplies those all together. So it becomes a number between 1 and 1,000. And we can then start to rank these. So there may be many different root causes and things like that. But FMEA helps us to find the dodgy ones first. That's what it's all about. So it's a very simple process, very structured, but it's very powerful. And it's been around for donkey's years. It was originally developed in the 1950s and 60s with the US Army and also with NASA over the space programs. There are many different RPM type arrangements there, and there are many standards as well. So it has developed. But what we're looking at here is how we might enhance FMEA later. And that's what Khadija is going to talk about. So FMEA is the start, but FMEA is also the living repository of corporate knowledge. FMEA, now it's taken on from just being a spreadsheet, is actually where we store all the knowledge, not just at the beginning, but as we start to get numeric values, as we start to build statistical models, that can all be stored in that FMEA. So next time we come and do this, next time we iterate the design, we're going to continually improve this. It's a repository of what works and what don't. Now, FMEA is all qualitative. And at some point, if we're going to identify risk, we need to put proper numbers to that. Remember how the confidence level came in? So we have to understand that every component is subjected to stresses and has its own inherent strength. Now, these are not single numbers, they're probability distributions. So different stresses have different probabilities. And the strength is our ability to withstand those stresses over time, not just for one-offs. And where these two overlap, that is the risk of failure that we're trying to set by our reliability target. So we need to understand what causes stress and what strength we have to resist it. So when we're looking about understanding strength, something that we need to do is we need to understand what materials are being used. We then need to know how are we going to test those to find parameters. We call those parametric tests. We're then going to look at what mathematical models might we use to represent those strengths and what parameters will fit them. And we're always interested in the variabilities and uncertainties because we need to get that confidence level calculated. Now, on the other hand, we also need to understand what stresses are there. So the first thing is, how are we going to profile usage? So in our case of the car, remember, we use proving grounds as a method of profiling. So how would we profile our nuclear fusion reactor? Maybe it's things like startup cycles, maybe it's shutdown cycles, maybe it's times at different temperatures or under different control strategies. How would we profile that to make it in something that's more manageable? Then in each of those, what constitutes damage? Is it load over area stress? Is it a thermal stress? Is it a thermomagnetic stress? Is it vibration energy? What would constitute damage and wear and usage? And then how would we go about calculating that parameter based on available data? Because it's very rare we can actually measure the parameter we want. We may have to infer it from other measurements. And then, of course, we need to really understand those variabilities and uncertainties in order to get the statistics right. So we do that by generating a physical test. So we've had parametric tests to understand materials and things, but when we talk about qualification, we're talking about components, subcomponents, and whole systems. So what will those physical tests look like? How do we qualify acceptability? So first of all, what qualification test will we need for our reactor? How would we simplify any test configuration to just concentrate on the thing we're after? How would we accelerate any aging effects if aging were the failure mode? And then how could we use this to help validate and verify our simulation model? What is it we're going to physically measure in order to start to verify our calculations? So for that, we use our simulation and we start to model the physical test. We simulate the physical test. That means we can look at the data from the physical test and we can verify our test and we can refine it, the model. Then, once we've got a refined model, we can start to simulate additional tests, which maybe we didn't have time or money to do. Lower priority tests, maybe with a lower risk priority number, but we want to still certify them anyway. So we can use our simulation to do additional testing. And we can also use our simulation to simulate the part in situ, our battery in a car rather than the battery on a shaker table, for example. So by then combining that physical test and virtual test, remember that's what leads us to the validation and the qualification. But at this point, we've only actually verified and validated a component. We've also got to consider how that component scales into the entire product. So we have to cascade local failure modes, which there may be hundreds, into full system by using systems of systems engineering. So this is where things like reliability block diagrams and model-based system engineering comes in. It helps us to generate fault trees for diagnosis purposes. And it also helps us to optimize maintenance schedules and ensure reliability growth, as well as qualifying that system. So all of this takes place at that stage. Now, of course, we're in a position where we can start to build real prototypes of our tokamak reactor and start to get real operational insight. So on the left, we're measuring data, and on the right, we're understanding strength again. So as data becomes available, we can measure that. Okay, data from different sensors we know has noise in, so let's clean that noise. We're not dumb. We know that there's lots of physics about this that we understand already. So let's apply that known physics. We know also that there's lots of data. So before we throw this to an AI engine as clueless ambition, let's already look at what we know and reduce any dimensionality. Now let's have a look at how we might calculate usage severity. So back to the other one, what constitutes damage? How do we calculate it? And then we can use this with existing physics and statistics and the new data-driven AI type approaches to help us develop new insight based on operational data. Now, at the same time we're doing that, we'll also be acquiring components which have been taken out of service. Some of them may have failed, some may not have done. But we can start to do forensic failure analysis and forensic analysis on those components. We can collate maintenance and failure data. We can perform FRACAS. For those who don't know, FRACAS is Failure Reporting Analysis and Corrective Action System. It's a database logging the failures and why they occurred. That means we can develop insight into the critical failure modes. That's then going to target our understanding of strength so we can improve our damage models by doing more parametric testing and so on, and developing new insight. And then ultimately, of course, these all come together in what we now call digital twins, or in digital passport. So a digital twin enables us to sort of model that onset of damage and how it's happening. Now, my little system here, I've got two different approaches. At the top, I've got a classification-based system. So this is using machine learning type classifiers. And what it's doing is actually novelty detection. If I've got 200,000 electric vehicles driving around, I can't go in on a Monday morning and pick one at random. I need a computer to say, this is worth looking at. I've not seen this before. So this is what classification does. It just looks for something which is anomalous, a novelty, an outlier, and said, you might want to look at this first. So it raises alerts. As we start to develop an understanding of what those mean, we can tag those data, those scenarios. And that's when we get to the more regression model just below it. And this way, again, we split it into two. We've got a mathematical model, which may be AI generated or really a physics informed AI type model, which is addressing usage severity. And we have a strength model, which is our statistical likelihood of failure. How close are we getting to the end point? And both of these can be fed differently. So what we're developing here is this digital passport for all of the products out there. It'll detect faults. It'll help us with improving our optimizing maintainability and things. It'll help us to calculate remaining useful life. And by that, we can qualify life extension. I first got involved in qualification of aerospace some years ago, and we were doing test flights on a refueling pod. And the first thing I asked the chief engineer when he went on site is, what's the first test that you're going to do? What's its objective? And he says, to get back to the ground as quickly and safely as possible. We'll take it from there after that. And that's very often what prototype testing is on expensive things. We may start it up and shut it down, and then we acquire data. And that gives us the qualification to do the next stop and the next bit and the next bit. So it's this iterative approach. So all of this can develop. Of course, we have to also consider, what do we do at the end? So this is where we get the reuse, remanufacture, recycle before we consider refuse. So really important if we've got nuclear irradiated components, for example, especially from a fission reactor, we don't want to be burying them easily. Reuse, remanufacture, recycle can come before that. So it all starts with FMEA, and FMEA is the start of this living repository of corporate knowledge and what works and what don't. So where is the shortfall of FMEA right now, and why am I so excited about what Khadija's working on? So if we look at a user story, this is one that I first have. I've got a reliability engineer, and he knows all about failure modes and effects. But he's probably forgotten about what the end customer requirements were, what the voice of business was suggesting, and what the regulator wants. They become lost in his concentration as the voice of engineer. So I would like a way that we can capture the voice of the customer, the business, the regulator, and the data and correlate them with our engineer's risk priority number, because this will ensure that all the important performance related product requirements are represented throughout the development of that product, not just the ones that our engineer is most familiar with. So again, what we're showing here is, how do we bring in those customer, business, regulator requirements and make sure that our test schedule at the end properly reflects them and our design reflects them. So that's really important to me. And the other thing that's really important to me is making sure that every requirement has a test. So before we release this product, we know for definite that we've tested it and that we're confident in that release. So here, a reliability engineer wants to correlate their technical requirements with their current testing activities in order to ensure all important requirements are adequately validated through the test plan and any additional tests are highlighted. So you'll see this diagram coming up in Khadija's presentation next. It's a matter of taking the customer requirements as well as the FMEA and bringing them in to make sure that our technical requirements encompass both. Then looking at those technical requirements and making sure we've got tests which properly exercise all of them. And by doing this, a bit like a pivot table really, we can then start to see, have we got all the test activities which properly address the customer requirements too. So I'm not very good at sticking to time. but hopefully I only overran by 3.5 minutes. So hopefully
You
that
did.
was a nice introduction into why what Kaji's doing is so important to what I want to represent and how it fits in that big picture.
Thank you,
Thanks, though.
Andrew. Thank you very much. And you did quite well, actually,
Better than I
regarding the
knew,
time.
better than usual.
So thank you very much. And I think people are appreciating. We're getting lots of applause on. So thank you. So you did very well, Andrew, sharing your screen through the Teams. I'm a bit cautious about that because I have to move around tools and the slides. So therefore, I will probably share my screen if that's okay with everybody. At this point, I'm going to share and I'm going to um, uh, uh, bring that we are. Let me look at my clock. 4 minutes behind the schedule, but it's fine. I think we have now break. We planned for till 11. So if people wants to have a break, please do so. But I don't want to lose you because I want to introduce the process and the tool, which I'm excited about. So please take a break if you want to grab a cup of tea, please do so, but please come back by 11 if you can. Thank you. And I'll stop my recording for a bit now. I'm going to explain um, the experience I've gathered during my PhD through the case study and the motivation for developing this tool. I also hope that Andrew has set up the background and complexity well. So as an academic, probably our job is to kind of simplify that complex process. Um, for those essentially who are not expert in the field or just emerging in the field and kind of trying to adopt those complex tool set, how they can go about it. So first, I will talk about the process a little bit, and then I'll demonstrate the tool we have developed. So the process Andrew presented, it's a similar sort of process that I have seen from the case study I did. So uh, the reason I say the process is complex, it's easy to draw a flow chart or a diagram like this, isn't it? And then it means we are showing where the data or information is flowing. Um, yeah, it's good that information is flowing, but are we making that flow easy? Is it keeping within the people or it is within the tool? Because if we look at this diagram, this is again based on a case study, that there are tools like QFD, if you know, quality function development, the tool, and then we have the FMEA, design FMEA, process FMEA, lots of, and then the FMEAs can have different levels, layers designed for components, for systems, and then the systems and systems. And then we also kind of, this diagram shows what are the consideration, the human involvement and decision making and so on. There are other tools like how those all of these FMEAs goes into a master document, the tool Andrew was talking about, and how that transfer to actually plan, which is often called DVPNR, another tool. So there are tools after tools and tools, isn't it? And I'm not going to go into very details, but what I am going to show that the give the background of the uh, main tools I have picked, or the concept I have picked from the other tools, existing tools, and why that was important to link them in a systematic way. So my hopefully my button will work. So the tools from this process I have picked are the QFT, FMEA, and then verification and validation plan. Another tool is called DVPNR. So These are the main tools I have looked closely into this process. By the way, this diagram, if you're interested, has been published and can be get. If you are interested, I can supply the document. So I picked this, as I said, from the process. This kind of concentrate on the three things. The reason on these three things is the QFD is the first, or also another form of representing QFD is they use a house of quality where they try to map the customer requirements with the technical requirements or technical specification. What they really want to do, that what customer wants, and how I design a product that meets those requirements. What are the specification of my products that's needed to meet these requirements? And this QFT or HUQ, House of Quality in this case, do that. And what it does also, a little bit of based on experience, people's understanding, and so on, they try to prioritize what are the specification of the product are most important from the customer's point of view. So they do sort of little bit of importance of the product specification. So from this analysis, list of technical requirements goes to the engineers who are more interested on the technical aspect of the risk aspect of the product, how to design the product, how to verify and validate the product, how do I make sure I designed a product that's gonna do what it does, as Andrew said previously. So usually, and ideal case, this all these technical requirements which has been identified early should be smoothly translated and transferred to the FMEA. And FMEA, failure mode effect analysis, should analyze those. And then, in an ideal case, ideal scenario, once we identify all those risks, based on the risk, we will identify what sort of mitigation activity we need, what sort of testing, verification, validation, or design chains, if there is any needed. And that helps us to plan the our verification validation. And another tool yet, design verification plan and reporting. So so this is the ideal, in an ideal world, this is how it should work. But the problem is, what I have seen from my case study is, um, this tool doesn't talk to each other. And um, and probably I have to acknowledge as well, the case study I did is a kind of large companies who has large department, and then different teams are dealing with different tools, different people are managing those tools. So and and then when this is managed by different people and the information flow or the data flow between this tool is not systematic, that what happens is the importance identified in the QFT is not correctly or accurately transferred, or even being transferred by the process of FMEA with the complex process and attention to the risk only, the risk priority number, as Andrew mentioned, the the importance of the customer tends to fade in. And often from the interview I have identified that um, the people who have very much have good understanding why that is risky, why technically that is risky, or how they have calculated the risk. But if I asked, okay, technologically you think if that functionality fails, there is a risk, how about the risk of failing the customer requirements? Do you know how that customer requirements links to the risk you are identifying? And often the answer was uh, no. So customer voice are not well understood when our focus is only on the DFMEA or FMEA, failure mode effect analysis. So that kind of brings to our attention where we are in a situation right now that we are developing new technologies, radical technologies. First of all, we don't need all the risk, identified risk for the new technology, because we haven't seen that. So it's kind of, we are being very creative and imaginative, and we are gathering all the people. But um, but the thing is, if we want to kind of focus on the risk, there are so many risks we can identify, isn't it? Because it's so uncertain. Then we kind of lost somewhere. So now where we should focus? Where should we focus? Should we focus on everything, or should we focus on the important thing? And how do we define that important or critical things? Of course, one thing is that I have to design or develop a product which is reliable, durable, safe, um, but also a product that's customer wants, and our legislation for low carbon and all sort of thing. So we cannot forget our the initial customer requirements, um, and we cannot directly need to understand, maybe it has been transferred somewhere, but we need to still understand what we are referring to. um, and when I talk about customer requirements in my tool, customer requirements are not the customer who are the end user. Customer could be your also I called is a voice of customer. I also call voice of business, is like the business what you want, and also voice of regulation, and which is very important currently, isn't it, for our transition um, to that new technology development or radical technology development. So based on this finding, what I try to do in my tool in a simpler form, we take, okay, we have the center of this FMEA where we identify the risk, and that's risks, and based on the number, we identify the top priority risks, which is higher the number of the risk, higher priorities it is. And then and we take that, but we also incorporate that with the importance of those functional requirements we identified, or technical requirements we identified in the QFT. So we take the importance from the customer points of view of the technical requirements, and we take the risk number from them, and then we merge them together, not in the DVPNR correctly. We have to go we extended that version a little bit to kind of map with the activity verification validation. In my case, I simplified is a testing, focused on testing, because there are many other ways you verify and validate your product. So the focused on testing here. So how do we map those again with the critical customer technical requirements, and put this understanding together, the importance, risk, and so on. We tend to find out which tests or which verification validation activities we need to focus on, what are the priority based on our understanding. And this is a tool essentially what's telling us not exactly what to do, but it is highlighting where the critical issues are. And then as a people, as engineer, you have the experience, you have expertise, and you are the person who is making the decision. So this tool is actually helping you to make the decision and actually analyzing. In my understanding, I think that test is top critical one. That should be the priority. Why this telling tool is telling me differently, if it is telling differently, or why the tool is identifying different test is having higher importance, why that is happening. So it's a another vehicle for you to think, not only just based on our previous understanding or experience. Is a tool helping you to make a decision or challenge our decision, or help our decision or challenge our experience, I would say. So this is the tool, and I explained what I did, and this is the process. This is the process where we did. So the first thing I want to highlight that the QFD is a different format, and again, QFD could be very those who you know, and many of you probably would know that QFD could be very in detailed, and then you can divide it into system level, subsystem level, and then you can go through the process, product process, and even in the manufacturing, you can do that. Similarly, for FMEA, you can do that. You can create FMEA for component level, you can do subsystem, and then systems level. Um, what we are proposing here is simple and is the very top level. So if we think about a product, a car, we are thinking of the top level, not going into the detail level. So we are thinking about the requirement of a, let's say we design, very simple case, we're designing a cup to drink my tea. What are the requirement for this? We are thinking about very simple process, and we can elaborate this, uh, but just to point out, this is system level. So the first one is based on the concept of QFT. It's not exactly QFT, but it is based on the QFT. We're using the concept of house of quality, where we take the key customer requirements, we map with the technical requirements that we think the product need. So this is the engineering knowledge. They would know what we need to design, what are the specification of the product, and they're gonna map using this tool that what customer says. And also customer requirements probably gives us a clue that what that product requirements should be, or technical requirements should be. And first we map them, identify how to map them, and then if there is any relation between that, if once we identify the relation, we can kind of put the importance or the strength of the relation. For example, like if it is a strong related, for example, I need to design a chair and the customer requirements is the chair cannot be heavier than that much. If that is a constraint, then probably the weight of the chair is a critical requirement and for technical requirement, and that needs to be maintained. So how strong that relationship is, we can define. Once we have done that bit of little calculation, which goes underneath, we identify which technical requirements are critical, and we identify the relative importance number. As engineer, we probably understand that all of these technical requirements are important from engineering point of view, but what are the relative importance from customer's point of view? So that gives us a importance number of the technical requirements, and then we transfer those technical requirements to the analysis sort of FMEA. Now, here to explain that, we take the concept of FMEA and failure mode effect analysis, which is, if you are familiar with, you know, and you can use. But if you don't know, we simplified the process again. We focused on in this. First, we identify the technical requirements from an engineering point of view. How critical is that? So we call it criticality analysis. If this fails, what will happen? So is the severity and the occurrence. How likely it can happen? It can fail. That's one thing. And if it fails, what's the consequence? And the importance of these two we put together to highlight the importance of technical requirements from engineering point of view. Once we have done that, what we do in the next stage is we map these technical requirements with the testing activities, because we identified the certain risks, and then risk could be managed again, that some we need to tackle, some we can just absorb, some we can just ignore. So again, based on your experience, you will identify what are the technical requirements you need to assess in a broader case. But for this tool, again, we are simplifying and we are saying we are analyzing each of the technical requirements, and we are identifying the risk of each of the technical requirements. And we also identifying what are the test verification validation testing we say, but here again I say the focus on testing. What are the tests we are going to do to kind of mitigate, that we can approve ourselves that the risk we've identified through the design change, whatever change, we actually can prove ourselves, demonstrate that this risk doesn't exist. There are many other tests we implement to identify actually the failure mode we have identified in FMEA is the actual failure mode. So we do physical test, and then the government physical test, legislation wise, which sector you are, standard, and all sorts of tests we have. So That's up to you how you decide, but we identified the testing activities you would need. Again, we simplified this process, identified the key testing activities for the system level, and then map them. Similar way we did for the QFT, we will map them in a such a way that we will emphasize if there is a test that is actually verifying, validating, or demonstrating whatever the reason is linked to the technical requirement. Once we establish the link, we can identify how strong the link is. More important to run the test to demonstrate, validate, and verify the technical requirements, more stronger the relationship is. And then we can choose that. We haven't gone through that detail, but we will go through that in the tool in a minute. And then once we have done that, this is the input from us. Once we have done that, what the tool will do for us, tool will produce this view for us. What it will do, that of course we have seen the customer requirements and technical requirements. This is mapped, and then technical requirements gets mapped with the testing activities, but we didn't map directly customer requirements with the testing activity. Because if asking, if the problem we have seen in the case study, that they know by the testing activities what are the testing they are doing, and what are the technical requirements they are validating, but they don't know what's the this test is actually doing a favor of which customer requirements exactly I'm validating. So I need a simpler way of telling that, okay, if we can map this tool will help us to do that. What it will do, it will map customer requirements with the testing activities. In that way, we will able to see from this support of this tool that how customer requirements are mapped with the testing activities. And then some testing activities we might find is not anyhow related to the customer requirements. We also will find that there are many tests we are actually doing to meet that customer requirements, and different strength we will also suggest based on the numbers you have input in here. And the tool again is a tool what has been calculated based on equations. Now you are the power, you have the power to make the decision, and it's tell that by looking at this value, looking at this number, and the priorities, you need to make a decision that, okay, the tool is telling me that four testing activities are linked to that customer requirements. Do we need to do that for test? Or in some cases, we have just doing one test for that critical customer requirements. Is it enough? So those sort of decision you can make using the tool. So it's a very quick explanation of the tool. Um, so what I'll do, can't see your comments or anything, unfortunately. But if you have any question at this point, please uh, feel free to ask. What I'm going to do is I'm going to now introduce the tool. That's probably my next task, isn't it? Let me move on. So the tool. So before I go to the live version of the tool, again, this is a few things I need to clarify. I did at the beginning. This is a demonstration tool. This is an academic developing a tool. So it's not a commercial tool. And there will be some limitations. And there are two purposes for the tool. One is taking you through the steps. So you see what are the steps we probably take. And the second is a simpler way to play with the idea. And our aim is that this tool will help you to understand the process, and a simple tool to demonstrate to your team, to yourself, and then think more. And then if you want to carry on the idea forward, so don't expect a full-blown customer um, um, tool that, as you will see in a minute. So for my Next, is there any question? Can you please the share link to the tool? Yes, I will in a minute. So what I need to do now, I need to go to the tool and itself. So I hope everybody can see the tool. Um, can you please give me a signal that if you can see the tool? Um, and can you see my screen? Okay, I'm probably missing something.
I can see the open learn create site. Is that what we're
Okay,
looking at?
yeah, that's great.
Okay.
Thank you, everybody. Okay. Now, the tool is launched in Open University's Open Learn Create platform. So this is the platform as Open University we use to launch our courses, tools, and is also freely available. Um, the reason why we have to use this tool, one thing is like it's on Open University's platform. Second thing is like to avoid some of the GDPR issues, and that has some limitations. That means that you actually have to log in. So, and I hope the process is not very cumbersome, but what you have to do, if you go to the link which I will share. You will find this tool, and then it's the introductory, what it is about, the description it will give you, and it will explain the steps you need to go through to use the tool. And once you have signed in, you probably have to enroll in this module. So one step is to sign in to Open Learn Create platform, and then the second is like enroll in this course, because in Open Learn Create there will be many courses, and then this is one of the, it is considered as one of the courses. So once you have enrolled, you should be able to see. So and also I have the lego for the funders, for the support. So the next thing, once you have seen this description, you can click on the content, and then it will explain. Because I have gone through the tool, it shows I have completed 100%, but as a they will treat you as a student, and they will show you the upgrade you do onto the tool. So if you click on this one, it should take you, it will be able to expand or collapse. The tool itself is here. If you get confused, it's just there. So if you click on that, it will take you to a background. It's we are not into the tool yet. It is a background. The reason again for this is like once we have many courses logged in. This is the site help you to manage. So for example, if I had 3, 4 courses logged in into OpenLearn, that will show here. But for you, probably you don't need to do that. What you need to just do is click on this, and then it is the tool here. Now I'll make it the tool full screen for our visibility, and I again the color wise and everything, uh, I'm not sure. I- I'm sure it's not the most user-friendly color, but if anyone has any problem seeing it, please let us know. So what I'm going to do now is demonstrate this tool step by step, using an example I have produced during my PhD. So it's a technical example, but that helps me to demonstrate it, because I couldn't produce a simpler one. So please bear with me. So what you have to do, you have to start. Okay, at the beginning, it just talks a little bit about what the tool is about. On the left side, you can see the steps. So so once I start, what is asking, again looking back to the process I have explained, it's asking what are the key customer requirements. And then we really emphasize that when you, if you want to play with this tool, play with the not only the customer who are the customer, your immediate consumer or the immediate customer, also consider the voice of regulation. And then again, the tool has very much limitation. We we can only hold seven customer requirements. Um, so I'm gonna again take a little bit of time to copy and paste the example I have created. So the first requirement for me is the operating cost. And it's an again example. I've seen the development of engine. The second requirements is the exhaust emission. Now, while I'm doing this, I'm going to talk about how they gather these customer requirements. Every industry has their own way of gathering the customer requirements. We are not on that end. We are considering and we are assuming you have already gathered the key customer requirements. So these are the 4 customer requirements I'm going to discuss now. And then once you have identified the customer requirements, what we are asking you to do is like think from the customer requirements or the voice of customer or the voice of regulation, what is the important, how important they think. One of the challenges I found from the case study, um, customer thinks everything is very important, and that's a issue. But how do you play with that importance and what is need and wish and all sorts of things? There are so many tools, but again, that's a different aspect. So, for example, for these cases, we have identified operating cost was a high importance, and the exhaust emission was very much important from the environmental point of view and legislation point of view. Power of speed wasn't so much as high as the other two, and they were sound power was very much important for some customer. So once we have done that, in this we move on to the next phase, where we identify the technical requirements. Similarly to the QFT, now you are thinking, what are the technical, the product specification, the requirements that the product needs. So the again from the engine example, sorry, while I'm just copying, um, I have identified technical requirements. One is maximum cylinder pressure, um, fuel consumption, and then the third one is the in cylinder pressure. I could populate all this data beforehand, but I thought going through the process would be useful. But please bear with me if you think otherwise. So and I'm trying to be uh, m- quick as I can. So these are the 5 technical requirements, probably from the engineering point of view we identified. So once you have identified that, then we're going to move to the next, where we are asking to do this sort of FME analysis. Again, there is a prompt that says if you do that FME analysis, then you will know what it means. But if you haven't done that before, if you're new to this field, not to worry. What we are asking to do is think that your technical requirement, if you think about the fail, if this technical requirement fails any of mode any way, um, you can think about many way that technical requirement fails. We have discarded that steps, but we are just thinking if that technical requirements fail, to simplify, what is the likelihood of failing, and if it fails, what's the severity. It's typical risk assessment process. So to do that, what we said, let's say, for example, again, it's just a demonstration example, may not reflect the real case, that we are identifying the maximum cylinder pressure. The likelihood of failing at this stage is medium, but if it fails, that has serious consequences of the safety, um, um, business reputation, customer satisfaction, so on, lots of things. So fuel consumption, for example, let's say the likelihood of happening that we don't meet the requirement of fuel consumption is very low, but if it does, then it has very much high consequences or severity. Similarly, we'll choose some value for this. Again, for each cylinder pressure, probably this is 9, low, but the severity is high. After treatment size is, if it happens, is uh, likelihood is medium, because we are not that developed, for example, and then its consequence is very high. And again, this one probably, let's say I'm just choosing that likelihood of happening is low and the consequence is very high. So once we have identified this, what it's doing, this tool at the site, will see that it's also highlighting some of the relative importance. So here, based on the based on your technical understanding on the risk, how important these technical requirements are. This is what you get essentially from FMEA, a little bit sophisticated manner, because the FMEA has a risk priority number and more details. Again, we can, if you want to implement this tool, you can again use that tool or use that number if that's necessary for you. So going to the next step, what we are trying to do now is actually we identified our customer requirements in our first step, and we identified our technical requirements. Now let's map them. So the mapping wise, again, this tool is helping. What are the customer requirements you identified? What are the technical requirements you identify on the top, or on the row? And then we again simplified. As Andrew said, you can have this qualitative understanding, and you can say low, high, medium, low, and you can give a range from 1 to 10, whatever. But to simplify, again, because the idea is to convey the knowledge, is we classified into three only. The sorry, four. If there is any relation, there is no relationship whatsoever you identify between the requirements and the technical specification. There is no relationship. If there is a relationship, how strong that relationship is it low, is it minimum, is it high? Again, that will depend of lots of your understanding about the product and your experience, and then people need to work together to determine this number. The well you determine the number, the well it reflects the relations and the output of this tool. So the idea is the team will be working together to define this. And so again, is the human is the in the process who is driving these tools, and tool is helping you to do that. So the customer requirements we have identified, and maximum cylinder pressure, and probably I'll just put the value that I have got in the example, and I'm not gonna explain the rationale for it. Probably it's not relevant to us anyway. So let's say for operating cost, I'm dealing with the customer requirements and how that is related to the specification of the engine. So there is, let's say five is the medium relationship with the fuel consumption, is a high relationship, and then cylinder pressure, let's say high, after treatment size is a low to no relationship, and engine emission is a medium relationship. So that's what I chose. So it's probably exercise for you to do with the team first, and then put the value in here. Similarly, I'm going to just choose the value I've got, and that helps me to check the output I've got. It's right. And for speed, I'm just choosing that how they are related. So 9, 5, 9, 5, what means is 9 means high, 5 means medium, and low is 3. This is how we defined the value for the relationship. Um, 9 and 1, and then sound pressure we've got, uh, doesn't really matter, um, but I'll do this anyway. So once we have established the relationship, um, then we can see that the weight of the technical requirements. So the weight of the technical requirements from the risk perspective we have seen in step 3. And in this one, we are looking at the importance of the technical requirements from the customer's point of view. And it's probably this bottom row are giving us the value, what we think based on the input you have given. Now we will move on to the next now step, where we identify the test. Because you identified the risk, you identified the importance. Now how are we going to mitigate those risks? And then the importance also was important. The importance of customer was important, because if legislation or standard or government is saying that you need to do the test to verify and validate your product, you have to think about that, regardless what is the risk showing in your FMEA or not. So you need to have that consideration in mind. So for example, after discussion with my team, I have identified the four um, key tests. The tests are heavy duty endurance cycle, and then thermal cycle, emission measurement, and transient machine cycle. So at this point, from engineering point of view, you identified what are the tests you require. Um, you probably also know from your experience that how important those tests are. How often when I did the case study, they know that test is very important. That's a critical test. And if I need to kind of, because my idea was to prioritize those tests, I asked, which test do you think among these four tests will be the highest priority or is the number one? And they often could say that one test that's the number one, but often there was two they think that's the number one, and so on. So my one question was like, you have hundreds of failure modes, you have almost hundreds of verification and validation, not the test but a different way of doing it, and then you have certain resources to do all of this. You have limited resource and time. So how do you prioritize those, and how do you prioritize the way you identify from the critical one, you identify the critical one from the just nice to have one? So how do you do that? So that's one of the aspects why we're looking at into this. So when I asked them, they said, okay, but this high duty endurance test was the high priority. Some of the thermal cycle was again probably not reflecting what you have seen, but let's say I'm just giving them some importance, and you will give the importance what you think for your application. So we have identified this test, high, medium for this test. Now, in this section, what we are now trying to do that we identify the technical requirements, we identified the test. Now let's map them. Now, the mapping, what we are trying to say here that we have these technical requirements, how we gonna verify and validate it through this test. Some of the failure modes, of course, underneath that why I need to do the test, because of that failure mode is so risky to fail. So now again, the similar concept of what we have done previously to map customer requirements with the technical requirements, similar concept what we're going to do is just saying if there is any relationship, identify that. So it could happen that there is no relationship between the technical requirements and the test we are considering. If there is no relationship, please put that. If there is a relationship, please put that, and then consider the strength of the relationship. Is like, is it that that test is necessary to validate that technical requirements? That test is not directly linked to that, but that technical requirements is tested because it's undergone through the test anyway. So there is alternative way or additional way we can do that, and it's useful to find that as well when you need to optimize your resource. So to do that, what we are going to do, we're going to set up the relationship. Again, I am just populating the value I have. So what I have got here is for maximum cylinder pressure, all of these tests looked very high importance. And then fuel consumption, I'm going to put the value I have got, 99 medium, and then no relationship, maybe, which is, I'm going to, again, is not representative. Maybe no, I'm going to say it may not be the representative value what you have said or seen. And then there is a low relationship, no relationship, is a high relationship, and then no relationship. So I have set up that, okay, individually each of the tests I have considered for all of these technical requirements, and I have set up the mapping. Once I have done that, is actually our input has been gone. If you remember the process I have seen, this is the based on the all the input I have given in from step 1 to 6. What we're going to produce in the next slide is the customer requirement and test mapping. Customer requirement and test mapping, what it is doing is like here the customer requirements initially you had, and hopefully you can still see my cursor, all the customer requirements you had, and it's mapping with the test which we didn't do before, and it directly maps based on the input you have given. And also it's showing the strength of this relationship. Again, it's is a bit different from the one strength we have seen in previous inputs, isn't it? We have seen just high, medium, low. Here we give the value and we give you the opportunity to play with it, because previously I defined high means 9, medium means 5, and low means 1. But you might want to decide that what that relationship. So we have set up some kind of predefined that the within these values are very important, and that value will represent the strength what we think from mathematical point of view. um, Based on this number you can change this number, and you can set up that what you think is the importance and so on, and then you can lower this number to kind of see um, play with these numbers, that what you want to set up your category, which category, which out of this value, which was is the high category from, let's say, 200 to 150, I think is the high strength. I want to set from 100 to 90 is the medium category, and then the lower. So this is the flexibility you will get. What is more interesting, I think, is the weight of the test. So previously, weighting of the test was, first thing I would say, I hope I'm right to say that there was no weighting in the FME anyway. There is no way you would know which test. Of course, you would know which failure mode has higher priority number, priority number, and based on that, if there was any test linked to that higher priority number, you would know that test is a high priority. But there was no way of calculating if 5 tests would have the same priority. How do you prioritize them again, isn't it? So I don't think previous tool did that. So we tried to do that again based on the mathematical calculation and so on. So we provide the test weights, and this value probably we don't need to understand much, uh, that why the number is 1.43. If you want to do that, of course you can go to the papers we have published. What we want to focus though is the ranking. So by doing that, we find a way, the tool is telling that this test, actually emission measurement, became the high priority test among these 4. This is the top priority one, the ranked one, sorry. The ranked one from our analysis is telling heavy duty endurance cycle is the number 2nd, transient machine cycle is 3rd, and then thermal cycle is 4. But don't trust the value produced. It's just a tool telling you both based on your analysis that this is what it looks like. Of course, you had an understanding in step 2 when you identify the critical sorry, step 5, that importance test in importance, and you knew that which test was important. So now try to see that if the tool is presenting differently or it matches the understanding you had. If it had, that's good. If it didn't, that why. And I would think the reason it didn't is probably it is considering the customer requirements and adding that value too. So challenge yourself that how I'm gonna use the tool to kind of rethink my importance of test. One thing also very much important, although in this example I realized that I did not produce, the data did not produce that there is no test has been identified that not meeting any of the customer requirements. So one thing to look at that, I have these customer requirements, I'm selling my product, and I'm saying that exhaust emission has been will meet your requirement. And how do I prove that? Because I have done this test, this test, this test, this test. So immediately from this tool, you can tell that this test has been gone through to validate my requirement. But then that this tool help you to do that. Also, if you find during the analysis that it has produced that none of the tests actually um, helping me to prove that I have the sound power, which was very important from my customer's point of view, but I'm not designing any test, not the case in here of course. But if the value was very zero or nearly zero or very low, that means like I'm not doing enough to prove myself that I'm gonna deliver this. So I'm gonna how I'm validating my product to my customer. So this tools is helping you to tell that strongly relate the customer requirements and the test, and challenging yourself to see, have I done enough? Have I done what I need to do? Or if I'm doing so many tests, then do I need to do it? Or heavy duty endurance test is very much significant. The reason is it's meeting all these customer requirements. So do I need to put invest on that and so on? So it's a kind of planning process, and ultimately you are the person who is designing and will be responsible to do this. So so it's in a collaborative way, you put the value before it, and you get the output based on the value you have input previously. So this is the tool. You can also kind of open up if you wanted to see in one screen that what you have done in step the mapping in step 4, which is kind of customer requirements. You can try to change. If I change, you can play with this tool, and if I say change, okay, I thought actually this was not a low relationship, but now I from the discussion I think it's high. If I do that, how my testing importance is changing. If I do that, is my testing importance changing, and so on. So you can play with this. Again, this is the customer requirements one. If you want to do with the technical and test table, you can similarly do that, change that, and you can see the importance if the importance has changed. Now based on my change that it's becoming this one is important, and it's just for you to prompt that why that is happening, why. So it also brings the idea that subjective understanding is like high and medium. Just changing one value can create a different result. Therefore we need to be very careful and collaborative thinking that how important people's knowledge, expertise, and choices are. So this tool essentially helping you to discuss or think about the steps you need to think. So if you decide to play with these tools, please do so. That will be really helping us to develop it further, expand, improve, and so on. So once you have done all of this, please, if you can give us some feedback, where we ask simple question that what do you think, how likely you're gonna adopt this process in your company, any benefit you have seen, or any comment. And of course, you can always contact me directly. You know my details. And that's it about the tool essentially. I gone through very quick, and I didn't see any chat or anything. Is there any question for me? I'm gonna move on to the next slide if I can, and it allows me to do so. Oops. So while we are doing this, um, uh, in the question asking session, I hope I didn't miss any slide, because my I've just, sorry, I'm just gonna check I haven't missed anything. No, I haven't. So what I'm gonna, while we open up the question asking session, I'm gonna request you again to give us some feedback. One, uh, what did you think about the process? While you can do this, we can start our question asking session. And as I said, if you need to reach out to me, any of the colleague in our Open University, and of course, and you, please get in touch, and we'll be really happy to help. So great. And any question, please, um, on the chat box, or you just can turn on your mic and then ask the question. I can see 10 people there, and I'm gonna be brave, and I'm gonna move on to the next slide to see how we did. If this tool allow me to. That's great. And while this is running, Andrew, do you want to come? If to kind of anyone has any question or anything, there is. Thank you very much. If I'm not sure if I'm pronouncing your name, Nur Kakum. Tool seems very useful. High level first phase activities. Concept would be useful for demonstrate. Yeah, thank you very much, Joanna. And if anyone has any question for Andrew, please feel free to ask. I know I took a little bit more time than I needed to be, or I planned to take, but I hope it was useful. And again, if there is anything you need to know about the article, the paper, the tool, um, or how we can kind of any problem in accessing the tool as well, please let us know.
I think from my view, so obviously I showed you that map of all the tools, and HBK, we through Encode and RelySoft, we provide those tools. So for me, one of the key things is it's linking the test and the FMEA together at the start is really important, because we don't want to find out towards the end that we've missed critical things. And that subjective approach that we're doing at this stage actually really helps. And there's going to be the test people in that meeting too, saying, you know, these are the tests we're doing. It's as much for trying to identify tests which are done historically but no longer serve purpose, which is quite common, and tests in particular that we probably need but we don't do because of other tests that we're forced to do, which aren't useful. So again, it spots that as well. But the other thing is to bring in that customer voice of the customer and everything. It's really important, because at the moment that voice, as you said, Kaja, is pretty much, it dies down to a slight whisper by the time the engineers put all of this effort into the FMEA. that tends to be the only thing that we concentrate on. So again, it's making sure that voice is heard all the way through the test. And it's not just qualification for tests, but making sure that they survive long enough, which obviously is part of what I do, but it's also making sure that we've got the tests that make sure it performs as it's supposed to as well. So it does what the customer wants, not, it's no good having a nuclear reactor which will last forever, but it doesn't actually produce any power. So it's all a matter of bringing all of those in, but having a structured way of doing it, which will persist long beyond this project, so that as we start to develop new replacement parts and improve it, that this is a good place to start. So I see this as very valuable.
Yeah, sorry to interrupt, Andrew, and thank you very much for your comment. I do realize people have to leave for the next meeting, so please feel free to leave. But if you want to stay, we are here. Andrew, if you need to leave, um, that's fine too. But I will wait a few minutes if there is any more questions. And thank you again very much for your support to run this webinar.
No, thank you.
Well,
Thank you for hosting it.
thank you very much.
Okay. Take care then, everybody. Bye.